Thank you. So, yeah, thank you, Subro. And I'm very happy to visit ICTS in Bangalore. Actually, this is my second visit. The first time was actually last year. There was some magnetism meeting here, but I could stay here only for 5 days or something because I was teaching that semester. But this time I will be here for 3 weeks, roughly. So I'm very happy, and I hope we can discuss with you. Okay, so I was asked to give some series of lectures. Then my subject is commensurability in quantum many-body systems, which gives some, as Subro mentioned, which gives some very general constraint on possible behavior of quantum many-body systems. Yeah, we have 3 days, this morning and tomorrow and day after. So today I'm giving a talk using slides. And actually, today I'm not planning to go into much of technical details, but rather I will give some historical overview of so-called Haldane gap problem, which probably most of you have heard about. But there's very interesting historical twist, which probably not many people realize. So actually, this part, I gave similar talk in several places in colloquium style. So even if you are not specialist in this field, I hope you can enjoy this. And tomorrow and day after, actually, I haven't fixed my plan, but probably I'm going to give some lecture on Blackboard on more technical detail. Okay. So let's start today's part. So today's talk may be titled as Berezensky-Kosterlitz Transition and Haldane gap phenomenon. And it's some hidden story behind Nobel Prize Physics in 2016. So probably all of you know that 3 years ago, Nobel Prize in Physics was given to these 3 people, David Saurez and Duncan Haldane and Michael Kosterlitz. And the citation for the prize was for theoretical discoveries of topological phase transitions and topological phase of matter. And okay, so maybe I should say, every year there is a news of Nobel Prize. And I used to be kind of cynical because, of course, prize doesn't change the scientific value of the discovery, you know. They, of course, did great things, but it's not because they got Nobel Prize, you know. They already did some great things. But 3 years ago, I heard a news. Then I was very happy because, of course, my research is closely related to what they did. Or basically, what I could do is just a small additional contribution to what they already did. And in particular, I have never written any paper with any of these people, but most of my scientific work is closely related to what Haldane did. And indeed, I met at least Duncan several times in workshop and so on. And this is in Benasque, and we went to hiking, and this is Duncan, and this is me. And also, this is in Corsica, Cauges, and this is Duncan, and this is me. So we shared some time. So yeah, I felt very happy. And yeah, also it's very good for our field, you know. So after 2016, I changed my stance. Okay, Nobel Prize is great. Anyway, and also, actually, probably you know that every year, Nobel Foundation publishes some background information for each prize. And there are 2 types. One is background information for general public, which is really for general public without much of technical details. But they also publish some scientific background for each Nobel Prize, more specifically directed to scientists. So this is very educational material, especially for prizes given to different fields. Like for me, astrophysics Nobel Prize, I can read this background scientific material, then I can learn a lot about important discoveries in different fields. So if you haven't, I recommend reading this material for Nobel Prizes, which you might be interested, especially in different fields. Okay, so this is for 2016. And so of course I knew a lot about this prize, but still I downloaded and tried to read. And then, they not only explain what these Nobel laureates did, but also they discuss development following their discovery. So they mentioned this Haldane phase discovery was led to more general physics of so-called symmetry protected topological phases. And then, I found some funnier paper. Oh, this is one of my favorites. So I was even more happy. Okay. Anyway, that's an advertisement part. Okay. So, as I mentioned, Nobel Prize Physics in 2016 was given to theoretical discoveries of topological phase transition and topological phases of matter. But in particular, there are three main important achievements for which the prize was given. The first one is so-called Kosterlitz or Berezinski-Kosterlitz transition. Actually, Berezinski in Soviet Union at that time found basically the same picture, even slightly earlier, but he died earlier. Maybe he died even in 1970s or something. So he couldn't get a prize, but anyway, he also made an important contribution. And the second topic was Haldane gap, which I mentioned in quantum spin chain. And the third topic is quantum Hall effect as topological quantization, the famous TKNN quantization. So my talk today is related to first two topics. And of course, the third one is also very important. You might say this is even more important, but today I'm not going to touch the third topic. And you might think, okay, this KT transition is of course important, and Haldane gap is of course important, but you might think these two are rather separate topics. But today I want to convince you that actually these two are very much closely related, at least historically. That's my point I want to make. So I prepared this as a colloquium talk, so there are some very elementary introduction. Maybe I can go this quickly, but so this Nobel Prize is concerned with topological phase transition. So first, we need to see what is a phase transition. So I guess most of you already know very well, but the typical example of phase transition can be found in magnet. Like in low temperature, all the spins are aligned to the same direction. And if you increase the temperature, then the direction of spin becomes very random. So this random direction of spin can be characterized by disordered phase, a paramagnetic phase. And at sufficiently low temperature, all the spins are pointing to the same direction, which is ordered phase. And in this case of magnets, this is called ferromagnetic phase. And change from this ordered ferromagnetic state and to disordered paramagnetic state does not occur completely continuously. Well, it's continuous, but there is a singular point. which is a critical point where this long-range order parameter vanishes at certain temperature, Curie temperature. And so this type of phase transition can be understood as spontaneous symmetry breaking. So for example, one of the canonical models to represent this kind of transition is Ising model, in which spin can point to up or down direction. So it has Z2 symmetry. And this ferromagnetic state breaks the Z2 spin inversion symmetry spontaneously. But this random paramagnetic state does not break the symmetry. So this phase transition point is where this Z2 symmetry is spontaneously broken. Then we can generalize this Ising model to models with continuous symmetry, like a XY model. So the XY model Hamiltonian can be written like this. The neighboring spins are interacting with each other, and the energy is given like this, inner product of vectors. And this is just a two-dimensional unit vector, which represents the direction of spin. And in this model, the spin can rotate in XY plane. That's why it's called XY model. So in this model, we can also expect similar phase diagram, although critical behaviors and so on are different from Ising model. But in low temperature, we can expect this U1 or O2 rotation symmetry is spontaneously broken, whereas in high temperature phase, this symmetry is not broken. And again, we can find a critical point where the spontaneous symmetry breaking happens. Okay. But actually, this scenario is known to be inapplicable to two dimensions. If we consider the model in two-dimensional space, like a plane, then this spontaneously broken symmetry phase cannot appear due to some rigorous theorem called Mermin-Wagner or Mermin-Wagner-Coleman. So I'm not going to discuss the proof, but you can prove rigorously that in two-dimensional model, this U1 symmetry or O2 symmetry cannot be broken spontaneously at any finite temperature. It can at zero temperature, but not at even very tiny temperature. This cannot happen. So this sounds like implying the absence of phase transition at finite temperature. But it's not really true, because this theorem just rules out the existence of the ordered phase with spontaneous breaking of U1 symmetry or long-range order. But it does not really exclude the existence of phase transition in general. And in fact, two-dimensional XI model is found to exhibit a new type of topological phase transition. Okay, now not new, but back in the 70s it was new. And this is what is called Berezhinsky-Kosterlitz transition. And okay, so this is again elementary, but because this becomes relevant in my latter half of my talk, so I quickly go through. So what was found by Berezhinsky and Kosterlitz and Saures was that the high temperature phase is similar. It's just disordered paramagnetic phase. But there is still phase transition at certain temperature. This is BKT transition temperature. And below this temperature, you don't have long-range order, but you have something called quasi-long-range order, which is characterized by the correlation function, which decays according to some power law. In contrast, at high temperature phase, the spin-spin correlation function as a function of distance decays exponentially, but in low temperature phase or BKT phase, the correlation function decays, but only according to the power law with some exponent eta. So this is 1 over distance to the power of eta. So this is important critical exponent. And okay, then maybe one question is how this transition is caused. So let's say you start from low temperature phase where correlation function decays only according to power law, but there is certain temperature above which the correlation function starts to decay exponentially. So what is causing this transition? And again, these three people, BKT, clarified what is happening at the transition. The answer is that BKT transition is driven by vortices. And because XY plane, XY spin can rotate on the plane, you can consider a topological defect, which is called vortex. So for example, this is a real space diagram of spin direction. So this is some center, and the spin can point like this way. So if you go around this center in some way, then spin direction also rotates. And this is called vortex. And also, you can consider spin compression in which when you go around the center, the spin direction also rotates, but in opposite direction. And if you draw the pattern of spins for that kind of compression, then you find this pattern. So this looks like a vortex. This doesn't quite look like vortex, but topologically they are very similar. Just the direction of rotation is reversed. So this is called anti-vortex. And if you have vortex and anti-vortex, then you can pair annihilate. Then you can be left with nothing. So again, I'm skipping detailed calculation, but you can show that if you put vortex and anti-vortex at certain distance, then there's an attractive interaction between vortex and anti-vortex, because they can pull each other, and then when they collide, they can pair annihilate to give nothing. That's lowest energy state. So there is an attractive interaction between vortex and anti-vortex. So BKT transition can be understood in the following. So in low temperature phase, there are some vortex and anti-vortex produced by thermal fluctuation. But in low temperature phase, they always form a pair because there is an attractive force between vortex and anti-vortex. So, so this is similar to usual gas of atoms like helium atoms or maybe hydrogen molecules and so on, because each atom consists of positively charged nuclei and a negatively charged electron, but they attract with each other and they form neutral atom or molecule. So from outside, you don't see any charged particle. So in this case, there are vortex and anti-vortex at small scale, but there is some binding force, so they always form a pair with some characteristic size. So if you look the physics at scale larger than the size of the vortex anti-vortex pair, then you don't see any vortex and anti-vortex. And in this case, we can derive this power law correlation function. But if you increase the temperature, then you have more and more vortices and anti-vortices. And at some point, there are too many vortices and anti-vortices so that you cannot distinguish any pair out of these lot of vortices, anti-vortices. At that point, vortices and anti-vortices dissociate from the pair, and then they start move freely. So this is, again, similar to what we found in real gas. So if you heat up the gas, any gas, to sufficiently high temperature, then at some point, electron will dissociate from atom or molecule, and that is called plasma state. So this high temperature phase is like a plasma of vortex and vortices and anti-vortices. And when this happens, again, I'm skipping the calculation, but we can derive the correlation function decaying exponentially. Basically, vortices and anti-vortices destroy this quasi-long-range order. So this is intuitive picture of BKT transition. And after their discovery, Kosterlitz again also made an important contribution by applying the renormalization group idea to this BKT transition. So this is again probably familiar to most of you, but back in 70s, renormalization group was just born. Modern concept of renormalization group was just born. And then this is one of the very early application of renormalization group. But I think still this is one of the most interesting and important applications of renormalization group to condensed matter physics. Yeah.
Was this renormalization group calculation also Berezynski's work?
No, I don't think Berezynski did RG. So yeah, I think Kosterlitz can claim this as a new contribution. So Berezynski, I think, gave this physical picture based on vortex and anti-vortex, but not RG. Yeah. So I think the earlier Kosterlitz-Saurez paper may be similar to slightly early Berezynski paper, but this is discussed in a single authored paper by Kosterlitz a bit later. Yeah, this is, I think, new. Yeah. Okay, so and I'm not going to, well, probably most of you are familiar with concept of renormalization group, but very briefly, you start from some model Hamiltonian at microscopic scale. Then you ask a question, what is the effective model Hamiltonian which describes slightly larger distance scale physics? And then you repeat this procedure. You start from microscopic Hamiltonian and then construct the effective Hamiltonian for slightly larger scale physics. And then you get the effective Hamiltonian. And from this effective Hamiltonian, you again construct the effective Hamiltonian for slightly larger scale physics. And you repeat this procedure. Then you see how effective Hamiltonian flows. And this can be plotted in this way, RG flow diagram. But precisely speaking, this space of effective Hamiltonian is infinite-dimensional, but this is kind of two-dimensional cut or projection. So this horizontal axis corresponds to the this power eta of spin-spin correlation function. And if you are familiar with Rattinger-Riggis theory, this is like a Rattinger parameter. And this vertical axis corresponds to vortex fluidity. So when vortex fluidity is 0, you don't have any vortex or anti-vortex. And for higher vortex fluidity, you will have a lot of vortices and anti-vortices. And your microscopic model is somewhere here. And if you do RG transformation, that is, if you look at slightly larger and larger energy scale, length scale, then effective Hamiltonian flows like this. So initially, the vortex fluidity is going to be suppressed. So this is this reflects the fact that the vortex and the anti-vortex attract with each other. So they tend to form pair. So once they form pair below your length scale, then you can forget about this vortex and anti-vortex. So by looking at larger and larger length scale, the vortex and anti-vortex drops out from the description because they form a pair. Okay, then it goes this way. And if this continues like this, then eventually vortex fluidity effectively becomes 0. So this is a situation which I explained for low temperature phase. So because all the vortices and anti-vortices form a pair of some size, so if you look at the sufficiently large scale, then there is no vortex or anti-vortex. Then the system can be described by this power law correlation function with some exponent eta. But this exponent eta depends on where you start from. So you have continuously varying critical exponent. Yeah.
In terms of the microscopic Hamiltonian,
Yeah, yeah.
What would be the eta parameter in that Hamiltonian?
Well, it's basically the strength of the coupling with respect to temperature. So very naively, you have this XI model J times S dot S, and the J over KBT determines this eta. I think we need some factor, but roughly like this, yeah.
I see. That's a dimensionless.
Yeah, because the J is interaction energy and over KBT, which, yeah. So okay, but if you start from this side, then initially the vortex fugacity decreases because of this pair formation. But if you repeat this transformation, then eventually vortex fugacity goes up. So if this happens, then system is eventually renormalized into infinite vortex fugacity, which means vortices is proliferating. Okay. So this limit represents a high temperature disorder phase. So the phase transition occurs exactly if you start from on this straight line. So if you are on this straight line, you are renormalized into this point. But if you are slightly away from this point to this way, then you are eventually renormalized into disordered high temperature fixed point. So this fixed line, not fixed line, but this line, on this line is the BKT transition point. And an important point, which is also discovered by Kosterlitz, was that starting from the BKT transition point, you are renormalized into this point, and we know the value of exponent at this point, which is 1/4 exactly. So for microscopic model, we cannot easily predict what is a critical temperature because it's not universal. It depends on the lattice shape and so on. But from this renormalization group analysis, what we know is that at phase transition, BKT transition point, this exponent eta must be 1/4. That is universal and exact result derived by Kosterlitz. And this was soon even confirmed experimentally because, okay, so 2D XY model I introduced as a model of magnetism. So in reality, however, it's not easy to fabricate such a two-dimensional XY spin model as a magnet, which may be possible, but it's difficult. But people realize that this 2D XY model can be actually effective model for helium-4 thin film. Because helium-4 is bosons, so at very low temperature, it becomes superfluid. And the superfluid is roughly Bose-Einstein condensed state with long-range, off-diagonal long-range order, which means that the wave function has some phase. And if all the particles, bosons, condense into the same quantum state, then you can define a macroscopic wave function like this. And then it has some phase. And if the phase is constant over entire system, then it's off-diagonal long-range order. But anyway, but at finite temperature, especially in 2 dimension, we can regard this amplitude to be roughly fixed, but this quantum mechanical phase of the wave function can fluctuate. So we are interested in how this phase variable fluctuate. And because this phase is 2π periodic variable, you can draw this, pictorize this phase as a direction on plane, and this arrow is rotating. And if you rotate this arrow by 2π, then it comes back to the original position. So this is really like a XY spin. So helium-4 thin film belongs to the same universality class as 2D XY classical spin model. Okay, so that's identification. And then so this is also a very interesting part, but I'm skipping the detailed discussion. But what people realized was that usually superfluid is associated with a long-range off-diagonal order, off-diagonal long-range order, which means that this phase variable theta is uniform basically throughout the system, but it's not really necessary for system to be superfluid. And what people found was that it's enough to have this quasi-long-range order or this correlation function to be power law. So if we have this situation, then system is still superfluid. But if this correlation function, that correlation function of e to I theta, becomes exponentially decaying, then we no longer have superfluid, and this becomes normal fluid. And moreover, what people found was that superfluid density, that is, you first entire liquid is moving at velocity v, and you suddenly stop the container, the pipe, but still some part of the liquid keeps flowing even after a very long time. And how much mass is flowing, that defines superfluid density. And the superfluid density can be directly related to this exponent eta. That's very remarkable result, which I don't explain, but you can derive this. And interestingly, except for this exponent, critical exponent eta, all the numbers we know exactly, because Boltzmann constant, temperature, mass of each helium atom, and also Planck constant. So everything else we know. Yeah.
So how is there an easy way to understand that the bare mass of the helium atom actually occurs in that expression?
Because this is kind of related to translational Galilean invariance of the system. So the kinetic term in the microscopic Hamiltonian directly shows up here. Yeah. Okay, so for this talk, I take this formula granted. Then you can derive very interesting result. That is, as I said, this eta critical exponent is non-universal. It can change as a function of temperature. But exactly at the critical point, or more precisely, this BKT transition minus infinitesimal value, then eta must be 1/4. Because eta, this exponent, exponent can change continuously depending on where you start from. But if you are at the BKT transition temperature, then eta must go to 1/4. So exactly at the transition point, we know the value of eta, which is 1/4. Then you plug in, then all the other quantity we know except maybe for temperature. So if you take the ratio, superfluid density over Tc at exactly at the critical point, then this ratio should be given by twice of mass square times the Boltzmann constant divided by pi h bar square. So this is universal number. So what this analysis implies is that the superfluid density, you start from low temperature phase and increase the temperature, then superfluid density decreases. But at the critical point, transition point, the superfluid density still has some finite value. Then you go infinitesimally above the critical point, then superfluid density drops to 0. So this implies a jump of the superfluid density in a universal way. So in this field, this is called a universal jump of the superfluid density. Then in this 1978 paper by Bishop and Lepi, they tried to verify this relation. And okay, so this is their experimental result. So this is one example experimental data. So the horizontal axis is temperature, and the vertical axis basically the superfluid density. And, okay, so this curve is something different. Dissipation, they are measuring dissipation, but anyway, so this is a superfluid density, so which decreases smoothly up to some temperature, then drops very suddenly to 0. So around this point is the superfluid temperature, transition temperature. But you see, it's not really discontinuous, but it's smooth curve. So you see, okay, it's not completely consistent with Kosterlitz analysis, but they also know why it's not completely discontinuous. That's because that analysis of universal jump assumes some static limit. That is, if you measure the superfluid density infinitely slowly, taking infinite amount of time, then the superfluid density should really drop to zero, at least theoretically. But in actual experiment, they shake the superfluid at certain frequency, then measure moment of inertia and so on, so on. But basically, the point is that in experiment, they use a finite time scale and a finite frequency. And later theory also accounted how the apparent superfluid density depends on the time scale of the measurement. And if you take this finite time scale measurement into account, then this sudden drop is replaced by this smooth curve. But theory can also quantitatively account how this is kind of smoothed out. And this solid line is this improved theory taking this finite time scale into account. So if you send this time scale to infinity, then this solid line curve converges to this dashed line, which represents a universal jump. So the theory and the experiment are actually consistent if you take this finite time scale into account. So if you extrapolate, you can estimate the exact phase one correct critical temperature and also how much jump in superfluid density you have. And then this is a lowest of Tc minus 0. And then you repeat this for many different samples. And then you can plot Tc versus this superfluid density just below Tc. And actually, Tc is not universal because this Tc depends on the thickness of the helium layer and so on, so on. So if you repeat same kind of experiment, every time you find different value of Tc. And also different value for this jump in superfluid density. But if you plot in this way, then all the data collapse into single line, straight line. And this straight line represents this constant ratio between these two quantities, which is just given by this number. So this relation was derived from BKT and Kosterlitz theory, and this agrees very well with experiment. So this is how this BKT transition was confirmed in this helium thin layer experiment. So I think this is still one of the most remarkable experiments verifying the exotic kind of phase transition. Okay, so this is already done in 1978. Yeah.
The critical exponent theta is sort of indirectly.
Yeah. So this relation was derived by assuming eta is 1/4 at that transition point. Yes.
But there's no other direct way to sort of see this power law.
Oh yeah, good question. Yeah, this probably not in this helium experiment. So if you can realize 2D XY magnet, then you can measure correlation function directly by neutron scattering and so on, which might have been done. I don't remember, but I think in this helium experiment, it's not easy to directly observe the correlation function. Yeah, this is sort of indirect. Okay, so this is about KT transition part, which probably you are familiar with, but this is old stuff. So I found, the young people recently are not necessarily familiar with this, but this is still, I think, very interesting. Okay, then I switch to my second topic, which at first might look very different, but eventually I want to demonstrate that this first part, BKT transition, and this stuff is very closely related. So the second part of my talk is about Haldane gap, so-called Haldane gap, which occurs in one-dimensional quantum Heisenberg antiferromagnet. So the Hamiltonian in question is just a very simple model like this. So you have quantum spins aligned on one-dimensional line, and then spins interacting with just the next one, Sj.Sj plus 1. And then this spin has three components, x1, xy, and z. So this is called Heisenberg model. And we consider antiferromagnet, meaning that this coupling constant J is positive. So classical mechanically speaking, the spin may be represented by some small arrow, unit vector. And because J is positive, classically, low energy configuration is given by one spin pointing, let's say, up, then next spin should point down, then up, down, up, down, up, down. That's called nail state. But it can be also, first spin can point to right, and then next spin left, and right, left, right, left. So there are infinite possibility for nail state, but classically the nail state alternating spin direction gives you ground state. But here we are concerned with quantum mechanical version of this model, in which each spin is really operator. Sx, Sy, Sg are all operators. So you cannot really draw the picture like arrow to represent spin. Then even the ground state is very non-trivial. So what is the ground state of this model? That's our first question. And indeed, this is a fundamental model in quantum magnetism, which has been studied for a long, long time, and still being studied. So the quantum spin can be characterized by so-called spin quantum number, or magnitude of spin, which can be 1/2, 1, 3/2, and so basically any integer or half integer. And for spin 1/2, even back in 1931, Bethe constructed so-called Bethe and that's famous exact solution for spin 1/2 version of this model. And well, you can solve exactly by Bethe and that for spin 1/2, but Bethe and that just gives you the exact wave function which represents the ground state. So to read off what's going on in this ground state or wave function is not so easy, but after Bethe's famous solution, for a long time people worked out what really this ground state wave function represents. And then what turned out was that in this ground state exact wave function, the spin-spin correlation function actually decays according to power law with some power eta. Okay, so for this model, actually this eta happens to be 1. But anyway, so if you look at this behavior of correlation function, so, well, this is like a critical state. And if you recall the first part of my talk, this behavior of correlation function is very similar to the low temperature phase of 2D classical XY model. And actually, this is not coincidence. And in some sense, these two models, even though they look very different, are essentially the same. So this already found out in early 80s, but in early 1980s, up to early 1980s, although you can define this model for any spin quantum number, any spin quantum number bigger than 1/2 had not been discussed much in the literature. Then there came a famous Haldane conjecture. What he conjectured was that actually the ground state behavior of the same simple Hamiltonian is very much different depending on whether the spin quantum number is half odd integer, like 1/2, 3/2, 5/2, or spin quantum number is integer, like 1 to 3. For half odd integer case, he basically argued that the ground state is gapless. So gapless means that you have ground state, then there is a continuum of excited states just above the ground state. So you can create excited states with arbitrarily small energy in the thermodynamic limit. So that's called gapless. And also spin-spin correlation function decays like a power law. Again, this is like a quantum critical behavior. And this is very similar or essentially identical to the low temperature phase, BKT phase of the classical 2D Xi model. In contrast, if spin quantum number is integer, then he argued that there must be non-zero gap above the ground state, which means that you need energy bigger than the gap to create any excited state above the ground state. And also spin-spin correlation function decays like exponential. And this is again similar to the high temperature phase of the classical 2D Xi model. And again, this is not coincidence. And they are very much related. Anyway, so this is what Haldane conjectured in early 1980s. And at that time, nobody expected this kind of stuff. So yeah, this was against the common sense of most of the people in the field. So that's why this prediction, which turned out to be correct, was called conjecture. Actually, I think in mathematician standard, 99% of what we do as theoretical fields is conjecture, I guess. So there is not much reason to pick out this Haldane's paper and just call this as a conjecture. But because people were suspicious of this Haldane's argument, so they started to call this conjecture. But Duncan Haldane himself doesn't like this name conjecture, so don't mention conjecture in front of him. Because basically he knew he was right. Okay. Anyway, okay. So then, okay, this is what he predicted, and then the question is how he reached this famous conjecture. That's the next question I want to discuss. And actually, my first paper, scientific paper, is something related to Haldane conjecture, and from contemporary viewpoint, it's something related to symmetry protected topological phase. But anyway, so as a student, I was exposed to this Haldane conjecture stuff. Then I learned through review and from some lectures how Haldane came to this conjecture. And you can find this story in many places. But as an example, this is a common story taken from Eduardo Fradkin's popular textbook, Field Theories of Condensed Matter Systems. And this is just an excerpt from this book. So according to this book, for half-integer spins, he means Duncan Haldane found that in addition to the sigma model, there is an extra term which changes the physics drastically. The extra term turned out to be proportional to a topological invariance. So this is something called a topological term of O3 nonlinear sigma model. So the common story was that Haldane Haldane first thought about this topological term of the O3 nonlinear sigma model. Then he realized this conjecture. That was a common explanation. And before going to this, maybe I should briefly explain what this topological term in O3 nonlinear sigma model means. So the O3 nonlinear sigma model is a field theory defined by this Lagrangian, where n is the three-component unit vector. And in path integral formulation of quantum mechanics, you do integration over dynamical field. In this case, this unit vector field n with the weight given by E2 minus action. And without topological term, the action of O3 nonlinear sigma model is just like this. And actually, if you discretize the space and time, this is like a classical two-dimensional Heisenberg model. So only with this term, this is very similar to what I discussed as 2D Xi model, but the only difference is that now the spin. So this is like a classical spin in path integral formulation. So this n vector field is 3-component unit vector. So it can point to x, y, and z direction and rotate. You can rotate using the 3-dimensional rotation. But other than that, only with this looks very much like a classical Heisenberg model, 2-dimensional classical Heisenberg model. But then there's a possibility of introducing so-called topological term, which comes into action like I times theta. Theta is called topological angle times some number q, and the q is defined in this way. And in terms of integral, this q looks like a bit complicated. But if you draw what this n dot d mu n cross d nu n means, actually this integrand represents the element within sphere. So this is like counting the area in the sphere or solid angle, which is spanned by this n vector field. So we have 2-dimensional space-time, x and tau, and you change x and tau, then this n vector can change the direction. Then it can span some solid angle on unit sphere. And if you do this integral and divide by 8 pi, then basically, well, without this factor 1 over 8 pi, basically you count how much solid angle you cover by sweeping x and tau, and the n vector changes the direction. And so it sweeps some area within on the unit sphere, and you can see the area on sphere or how much solid angle you sweep. And if you divide by, okay, maybe 1/2 is, 1/2 of this is solid angle. And if you put this factor, then this number q measures how many times you sweep the sphere by changing x and tau over entire spacetime. So this q, under appropriate boundary condition, represents something like a winding number of sphere. So how many times you cover entire sphere if you move around the spacetime. And this is quantized to be integer. And this is some sort of topological quantum number, winding number. So general O3 nonlinear sigma model is given by this type of action, including both non-topological and topological term, and then do this integral. Then you obtain the partition function. Sorry, so here I'm considering 1 plus 1D spacetime. Yeah.
I said that 2 plus 1.
Oh, you are talking about 2 plus 1D. Well, yeah, that's another story. Yeah, also in 2 plus 1D, you can also consider generalization of this term. But then the effect is very different.
That term survive under RG because there you will have some like extra dimensions. So you will have some like.
Oh, you mean dimensional counting? Yeah, if you just naively generalize this to higher dimension, perhaps yes. Yeah. But there are other things you can do for generalization. But yeah, in 1 plus 1D, this is the scale naive engineered dimension is same as this one. So if you don't have this topological term, as I mentioned, this theory is essentially equivalent to 2D classical Heisenberg model. And what we know, okay, it's not yet mathematically laboriously proven, but what people believe is that 2D classical Heisenberg model, unlike 2D XY model, classical XY model, which I discussed, and XY model has BKT transition at finite temperature. But once you generalize this to Heisenberg model with 3 components, then for any finite temperature, non-zero temperature, we believe that this model is always disordered. So always exponentially decaying correlation function. And if you start from, okay, so another thing is that, so this is the O3 nonlinear sigma model action with a topological term. But what you can find in textbook and so on is that this parameter theta, topological angle, if you start from quantum spin chain, then this topological angle is related to the spin quantum number, S, like a 2 pi times S. So that means that if spin is integer 1, 2, 3, then topological angle is 2 pi times integer. And if you do this path integral, then this action can be decomposed into this way. Then the effective topological term is like this. So the weight is always exponential of action. So if you have this topological term in the action, the effect is the some phase factor e to power I theta times q. But this theta is given like this. So e to I theta times q can be written like a -1 to the power of 2s times q. Okay. That's important. And if my spin quantum number is integer, this becomes a -1 to even number times q. Q is a winding number which is integer. So so -1 to even power is always 1. So that means that if your spin is integer, you can derive this nonlinear sigma model with topological term. But at the end of the day, this topological term does not affect the physics. You can basically ignore as long as you consider the bulk. If you have boundary, then there is something interesting can happen. But for bulk property, you can forget. Then the theory can be reduced to O3 nonlinear sigma model without topological term. And if topological term does not contribute, and you can be reduced to O3 nonlinear sigma model without topological term, then the behavior is like a 2D classical Heisenberg model, for which we believe that the system is always disordered and the spin-spin correlation function decays always exponentially. So that gives you the half of the Haldane conjecture that for integer spin chain, you always have disordered exponentially decaying correlation function. So from this standpoint, the integer spin chain is in some sense simpler or easier because you can ignore the topological term. But this part was difficult to accept for most people, especially condensed matter physicists in early 80s. Because people knew that the spin 1/2 is gapless and it has power law correlation function. So what Haldane conjecture according to standard textbook works like this. So for half integer chain, half of the integer spin chain, like a 1/2, 3/2, 5/2, this phase factor due to topological term, e to I theta q becomes -1 to odd integer times q, which can be rewritten as a -1 to topological charge or winding number q. So this is non-trivial phase factor because you can consider, well, if you do path integral, you have configuration with even winding number and odd winding number, and then they contribute with different signs. So this is something you don't have in classical spin model. So this is really quantum effect. You can call this phase as a Berry phase or something, if you like. So this is genuinely quantum mechanical system for which it's difficult to predict from field theory, at least in standard technique. But the argument is like for spin 1/2 from Bethe-Ansatz exact solution, we know that the system is gapless and also power law decay correlation function, the system is critical. And because all the half odd integer spin chains can be described as the same effective theory, all half odd integer spin chains should be critical, gapless and the power law decay correlation function. That's kind of argument because of the topological term. So actually from field theory point of view, this part is very tricky. Maybe if you just show this to field theorists, maybe they don't believe this part, but maybe they easily accept this part. but in magnetism or condensed matter physics in early 80s, this part was taken for granted, but this part was hard to accept for most people. So that's interesting twist. Yeah.
The topological angle theta is equal to 2πs, that comes from path integral from the derivation of...
Yeah, so there are several derivations. You can do Hamiltonian derivation or path integral derivation. Yeah, I will later come to this point. But one thing worth to note is that actually you can also change this topological angle continuously by changing the Hamiltonian. So here we assume the uniform chain with the same exchange coupling everywhere. But you can introduce bond alternation, which is you put strong bond here, next bond weak, strong, weak, strong, weak. If you introduce that kind of variation, then actually this topological angle can be changed continuously as a function of this alternation. So actually later people did study such model numerically. And what happens is that actually this argument turns out to be correct. That is, this nonlinear sigma model is gapless only when this topological angle is pi modulo 2 pi. So if you change bond alternation, theta changes continuously, and whenever theta hits pi or 3 pi or 5 pi, the system becomes critical. So you can observe several successive quantum critical points, and that has been confirmed numerically. Yeah. So in the end, this argument, although kind of tricky, turns out to be correct. Yeah. And you can also change topological angle continuously by introducing bond alternation.
In those cases, there's no RG flow?
Well, so, yeah, so only at theta equals pi, it goes to some critical point. And away from theta equals pi, it goes to yeah. So you can draw RG diagram in theta something plane, yeah. Okay, so, okay, that's the story when I was a student in early 90s, I kind of learned about this stuff, but I was kind of wondering, because this is nice, but still the question remains, how did Duncan Haldane come up with this kind of idea? Because as I explained, this nonlinear single model topological term approach relies heavily on concepts from high energy physics, nonlinear sigma model and also topological term. And nowadays, if you walk into random condensed matter theorists, let's say in ICTS, like Subro, he can talk about topological term and so on, blah, blah, blah. But back in early 80s, the situation was very different. I think very few condensed matter people talked about this kind of stuff. But still Haldane came up with this, and how, that was my question. And in fact, there are many people working now in condensed matter physics, like Fradkin and Xiaoguang Wen and Ian Affleck and so on, who are originally from high energy physics. You can find many of them these days. But Duncan himself actually started in condensed matter theory, and his PhD thesis was in '78, and actually he was a student of Philip Anderson, and titled his PhD thesis like extension of Anderson model as a model for mixed valence rare earth materials. So sounds very much like condensed matter physics, or maybe solid state physics. Okay, so I was kind of wondering how he came up to this, okay. Then I had the opportunity to interview Duncan, and I asked this question: how did you come up with this idea? Then I got some very surprising answer, at least for me. That is, I learned all this stuff about O3 nonlinear sigma model and topological term. That was the basis of Haldane's famous Haldane conjecture. But actually, at least historically, this is not true. So it's not with this topological term stuff he came up to this Haldane conjecture. And what he explained to me was that what really happened was that he came up to this Haldane conjecture, although he doesn't like to be called conjecture, but so he found this Haldane gap based on Topological liquid theory, not with topological term. This was very surprising for me because I have been working on this Haldane gap business for many, many years, but I had never heard about this until that point. So what happened? So that was very interesting. So, okay, so let's go back to the history a little bit. And after Haldane made a famous conjecture, as I said, at that time, very few people believed this. But then Haldane's conjecture was confirmed by numerical calculation by these people, Vortex and Julien. They were physicists in France. And this excerpt from this paper, their paper. Okay, so, if we consider hypothetical situation, which is probably almost impossible, but if nobody knew about Haldane gap until now in 21st century, and then Haldane wrote a paper, let's suppose, then you can download some, open source software somewhere and do the DMRG up to 100, 200 sites and immediately find the Haldane gap. But in early 1980s, the situation was very different. So numerical approach to spin chain was developed a little bit, but still not so widespread. So these people tried to study spin one chain by exact diagonalization up to 12 sites. So again, this is nowadays pretty easy. You can do in 10, 15 minutes by downloading some software and input parameter. But at that time, this was kind of cutting edge computational physics study. So they basically found a gap, and okay, so I don't have time to explain about this plot, but they extrapolated from 8 to 12 sites. And basically their conclusion is that the prediction of Haldane about the different behaviors of integer and half-integer spin chains are here completely confirmed. That's their statement. But I heard that even after their paper, many people remained suspicious, saying maybe their, finite size scaling analysis is wrong and so on and so on. But anyway, at least these people claim that the Haldane conjecture was confirmed numerically. Then, okay, we should look at this reference number 4. That's supposed to be original reference of Haldane conjecture. So here you can find a bulletin of American Physical Societies. I think this is just an abstract or something of APS meeting, so not very informative. Then they also cite ILL report number SP8195, unpublished. So what is ILL report? That's the next question. So ILL stands for Institut Laue-Langevin, which is a research institute in Grenoble and France. So they have a neutron reactor, so they have magnetism group, and they have theory group. And Duncan Haldane was a postdoc there for a few years after getting PhD in Cambridge. And ILL report means preprint issued by ILL. Then the next question, which might sound dumb, but still, next question I want to ask is, what is a preprint? Okay. So maybe even now we don't use the word preprint anymore, maybe, but when we talk about a preprint, maybe most of, especially younger generation, probably think about this archive.org. But this is sometimes called preprint server. But this preprint server started in 1991. And the condensed matter section started only in 1992. And this Haldane's paper was in 81. So 10 years before this preprint server started. So it cannot be on archive at that time. It was impossible because it didn't exist. But my point is that, okay, so probably unknown to younger people is that even before archive started, it was customary among physics people to circulate drafts or unpublished papers by postal mail. Do you remember postal mail? And this distribution was done on individual basis, like you print few extra copies and send to your friend. Or some institute did this more systematically. So if you belong to some institute, you can submit manuscript to institute, then there is somebody takes care of printing several copies and send out to some other institute. And actually, I spent 2 years at my current institute, ISSP, Institute for Solid-State Physics of University of Tokyo. And ISSP had a similar system. So at that time, it's called a Technical Report of ISSP Series A. Actually, this Series A was a preprint. So when we wrote a paper, before publication, we could print some copies by submitting to ISSP, and they put some nice cover and print extra copies. And this is one of the earlier preprint from 1960, written by Yoshida and Miwa. And Yoshida is Y of RKKY interaction, so pretty well-known physicist in Japan. And this is an insight. Well, actually, I was impressed because this was back in 1960s. So we didn't have tech, of course, but apparently ISSP has some typesetters, so they could typeset equation rather nicely. So if you go to ISSP library, you can still find this. And also, yeah, this is one of my early papers, and so I made it to this ISSP preprint, Technical Report Series A, back in '94. I think this is my only one. And of course, this practice discontinued after some years. Okay, so this time already archive started, but Contomat already existed, but maybe not so widespread at that time. But after some years, around year 2000, of course, most people were using archive. So this Technical Report Series A was discontinued around 2000. But still, you can go to ISSP library and find those back numbers. Okay, that's explanation of preprint. Yeah.
Preprint request cards.
Mm-hmm. Oh, yeah. I only saw a few, but yes, that kind of system existed. Okay. Okay, so IRL report, which Haldane wrote, the original paper of Haldane conjecture, was circulated as IRL report in a similar way. So what happened to this IRL report? So the interesting story is that this IRL report was, of course, submitted to some journal, according to Duncan. But then he got some report, which said this is in manifest contradiction with fundamental principle of physics, then rejected from journal. And I think he said that he sent to maybe few different journals or something, but eventually it was rejected and not published. Then, interestingly, Duncan Haldane himself also lost this draft. And as I said, this is before the LaTeX era, so maybe if you lose the paper draft, then maybe it's gone. Okay. And then somebody asked IRL library whether if they hold this old preprint, like ISSP. But then answer was that at some point, I moved library from old building to new building. And in that course, they discarded old unnecessary documents. So all the old preprints were lost. So very interestingly, the very original paper of the Nobel Prize winning work of Haldane gap was completely lost from human civilization for many years. Okay, so yeah, actually shortly after this, interview, I met my colleague Andreas Honecker, who is originally from Germany but now working in France. And we talked about this. And actually, he is who tried to find the old preprint of Haldane some time ago, even before the Nobel Prize. But he couldn't find because of this IRL moving the library. But we talked about this, and we promised to renew the effort to find this preprint. And I couldn't, but maybe he contacted several people. And eventually, it was found out that Jenő Sorion, who is a physicist in Hungary, Hungarian Academy of Science, he's also author of some textbook on one-dimensional physics. And he had this Haldane's old preprint somewhere in his drawer or something. And so finally, after Nobel Prize in 2016, shortly after the Nobel Prize, he found this old preprint finally and sent it back to Duncan Haldane. And then, okay, so this is a copy of the original preprint. And yeah, so Haldane Institute, Laue Langevin, and the ground state properties of blah, 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 blah. And yeah, this is IRL preprint, SP8195. Okay, so here he wrote to be submitted to physical regulators, but apparently PRL rejected. Yeah, in retrospect, it's very stupid, but still, okay. Well, yeah, actually, on the title it says nonlinear sigma model, but as I hope I will explain, the content is not really about O3 nonlinear sigma model. Anyway, and this is the equation which I picked out from, yeah, so yeah, this is the model he studied in this preprint. Okay, then Duncan finally got back his old draft. Then maybe he asked somebody to typeset this old preprint in LaTeX. So if you go to archive now, then you can find this 1612 00076. So this is a LaTeX typeset version of his lost preprint. So now everybody can look at this old paper. So yeah, I think this Haldane gap is very interesting scientifically, but also this shows interesting evolution of scientific communication in physics. You know, so in 80s we didn't have archive and we didn't have LaTeX and so on, so on. So you can write a paper, but if it is not accepted, it could be lost, even if it is Nobel Prize winning work. But now, at least you can submit to archive, and as we know, this Perelman's famous proof of Poincaré conjecture is never published, just on archive, but it doesn't really matter. Yeah, okay. So, interesting, well, this is a side remark, but this is the Nobel Museum in downtown Stockholm. So I visited there maybe in 2017 or something with my bike. Anyway, so this is a small museum, but this is an entrance. And maybe they rotate the exhibition, so I'm not sure they are still displaying this. But once you're inside, you can find a panel of Nobel Physics Prize in 2016, and they explain something. And so there is some glass case which displays several things. And actually, it turns out that if you win a Nobel Prize, then this Nobel Museum would ask you to send one memorabilia, so which can be anything, which can be related to research, or in case of some laureates, they send some childhood memory stuff. And yeah, but in case of Duncan Haldane, he sent this lost preprint, which was rescued by Sorion. So in the glass case, so yeah, this paper is actually the Duncan's lost paper, and now it's displayed in Nobel Museum with some explanation board. And by the way, I also find this paper on this display. This is, if you remember, this is a temperature, and this is a superfluid density just at the critical point. So this is experimental data confirming Kosterlitz RG transition, which is also part of the Nobel Prize in 2016. I think this is what Kosterlitz sent to Nobel Museum. So this plot was by experimentalists, I guess, but the experimentalists gave this to Kosterlitz, then Kosterlitz gave this to Nobel Museum. Okay. So maybe yeah.
Anybody find out who the referee was?
Pardon me?
Anybody find out who the referee was?
Nobody really know, but what I heard was that actually this Yeno Sorion, who did keep this Haldane paper, he was a vocal critic of Haldane conjecture for a long time. So he could be referee, but yeah, I don't know. There are too many people who didn't believe Haldane around that time. So I don't know. But I guess physical review at least keeps the record. So maybe for 50 years or something, they should keep this secret, but maybe at some point they can release the identity. Yeah, that could be interesting. But okay. So, okay, then, yeah, I want to explain very quickly how actually Haldane came up with this Haldane conjecture and how his original argument was related to this BKT transition. So actually in
XXC deformation derivation,
yeah.
it was basically known from the work of Jan Andrik, etc.
Yeah, okay. Well, in some sense, yeah. But I'm trying to explain, yeah, following his original, yeah. Well, in some sense, yes, it's known by now, but yeah. Okay, so he, okay, yeah, so this is an excerpt from this original lost paper of Haldane. Actually, he generalized this Heisenberg model to so-called XXG chain by introducing this coupling lambda to this chain. So with this parameter lambda, generally this only has U1 symmetry, and only at lambda equals 1, you recover Heisenberg chain. But this generalization is kind of useful. And okay, so I'm using the parameter delta, the same thing, but a different notation. So then, yeah, he started from this XXZ chain with this parameter delta, and eventually he considered the limit of delta goes to 1, which reproduces the Haldane, the Heisenberg chain. And so this XXG chain is also exactly solvable by Bethe ansatz, and by many years of study, including Duncan Haldane himself, the ground state phase diagram of this model was pretty much well understood. And the picture looks like this. So this horizontal axis is delta, and between delta equals -1 and the delta equals 1, there is a critical region, which is described by so-called Tomonaga-Rattinger-Likit. And this green region, critical region, is also very similar to classical 2D Tomonaga-Rattinger-Likit, classical 2D XI model. And so belongs to the same universality class. And essentially that behavior is called Tomonaga-Rattinger-Likit. And using the exact Bethe ansatz solution of this XXG chain, the critical exponent eta, if you remember, this is a power of correlation function s dot s at large distance, 1 over distance to power of eta. And this correlation exponent eta was also found out exactly as a function of delta. So if you put delta equals to -1, then arc cosine inverse of 1 minus 1 is like pi. So eta becomes 1 minus pi over pi. That goes to 0. So if you reach this limit of delta equals to minus 1, which actually is identical to Heisenberg ferromagnet, eta goes to 0. But if you increase delta, and when you approach delta equals 1, arc cosine of 1 is 0. So eta becomes 1 minus 0 is 1. So eta changes continuously from 0 to 1 in this region. That is what was known for spin 1/2 XXG chain. But I think what is important and what is noticed only by Duncan Haldane at that time was that if you compare this with the phase diagram of the classical 2D Xi model, which I explained the first half, you see something very strange. It's strange because, as I emphasized, in classical 2D Xi model, eta also changes continuously by changing the temperature microscopic parameter. But eta can increase only up to eta can increase only up to 1/4. And beyond 1/4, you have proliferation of vortices and you have gapped phase. So this is what I emphasize, and this is what was even confirmed in this helium thin film experiment. But in this XXG chain, quantum spin 1/2 XXG chain, eta changes from 0 up to 1. So somewhere this eta passes, exceeds 1/4, but still remains critical, gapless. So they are quite different. So the Haldane's question was why you can reach eta equals 1 in quantum case, although you can only reach up to eta equals 1/4 in classical 2D Xi model. That was the essential question. Yeah, actually, before this Haldane gap paper, there is another famous paper by Haldane that is this Latinger-Rigid theory of 1D quantum fluids and blah, blah, blah. So here, actually, this is already important paper, but this gave this became a setup for the later Haldane gap discovery. Okay. So as I said, quantum spin is different from classical spin, but it's also compact in the sense that if you rotate spin by angle 2 pi, then it comes back to the original position. So you should be able to define vortex in 1+1D space-time. Then you can expect BKT transition. But in the classical 2D Xi model, the low temperature phase is stable only when eta is equal or less than 1/4, according to Kosterlitz RG analysis. But in case of quantum spin 1/2 XXG chain, the low temperature, the critical phase is essentially the same as a low temperature phase of classical 2D Xi model, but somehow eta can survive up to 1. So there's a range of parameter between eta 1/4 and 1. Only this quantum spin 1/2 chain is stable, whereas classical 2D Xi model is not. So the question is why this quantum spin 1/2 chain is more stable. That's a question Haldane tried to answer. And actually, if you go through the calculation in the original paper, the lost paper, there is some sort of answer, but it's not very intuitive. So I'm introducing a more intuitive version of the argument which was given by Duncan himself to me. And also he gave this explanation very briefly in his Nobel lecture at the time of this award ceremony. Although it was very quick, so very brief, so maybe few people could understand what he meant, but so I'm trying to explain. So the bottom line is that it was vortex and anti-vortex vortex proliferation that drove this BKT transition. So that was reason of instability. The bottom line is that in case of quantum spin-1 half chain, which is my current interest, this fundamental vortex with winding number 1, like shown in this picture, is actually forbidden by quantum mechanical reason. And only double vortex, that is spin goes around twice when you go around some center of vortex, is allowed. So this extends the range of stability because double vortex is more difficult to produce, so to speak. Yeah, I am going to explain, but I first giving the statement, then explain why it's forbidden. Okay, so this is his explanation. So, sorry, some Japanese still remaining, but so this is a space-time picture of the spin chain. So in spin chain, we have only spins on discrete sites in the space. But if you do a path integral formulation or something, we should consider this space-time. By the way, this battery is off, so maybe I use this. Okay, so vortex. So this is fundamental vortex with winding number 1 can be pictorialized like this. So each spin evolves over time, and if the time evolution of each spin, so this is time evolution of this spin, and this is time evolution of this spin, and so on. And each spin evolve over time in this way, then you find a vortex in space-time, okay? And now I consider moving away. So in this picture, the center of vortex is here. Because if you go around this star, the direction spin rotates by 2 pi. So now I consider moving this center of vortex to next side, or the vortex is always in somewhere in between side, but you can consider moving this center of vortex to next bond here. Then let's consider what happens. So if we look at the spin, which is farther away from the vortex, then moving this vortex center from here to there doesn't change much about this. So the angle of this spin may be tilted slightly, but not much difference. So away from the center of vortex, there is not much change, but there is one spin which is affected very significantly by moving the vortex center from here to there. That is this particular spin, which is sandwiched between old location, original location vortex, and a new location vortex. Because if in the original vortex configuration, in which the center is located here, so this spin is rotating like this. So the counter clockwise, starting from this time to this time, this spin rotates counterclockwise like this. But once this vortex center moves to this place, then this spin becomes left-hand side of the vortex center. Then now this spin must rotate like this spin. So this spin rotates clockwise. So after moving this vortex center to this place, this spin used to rotate like a counterclockwise, but now after moving the vortex center, this spin must rotate like clockwise. But of course, the initial state spin is pointing to right, and the final state spin is pointing to left. That's the same. So the counterclockwise or clockwise, it must rotate pi. So the final state doesn't matter. So it seems like it doesn't matter much. But as you know, in quantum mechanics, it does matter. Because the difference between counterclockwise pi rotation and the clockwise pi rotation amounts to 2 pi rotation. And the 2 pi rotation spin seems to do nothing, but in quantum mechanics, if you rotate spin 1/2 by 2 pi, you get phase -1. So more generally, you can get, so you start from some correlation and end up with some correlation, but you can pick up geometrical phase factor called Berry phase. And in case of spin 1/2, you can pick up phase pi or minus sign. And for any half odd integer spin, you have the same effect. So if spin is 3/2 or 5/2, you can do the same, and the difference between pi rotation clockwise and the counterclockwise gives you phase factor pi, so you get the -5. So in this case, just by moving vortex center to the next site, you get the same wave function, but with minus sign, so they cancel each other. So that's why in path integral, this fundamental vortex configuration with unit winding number doesn't appear. So in that case, in that sense, this fundamental vortex is forbidden from the theory. Later, yeah. And okay, so what happens for spin 1/2 and 3/2? And okay, so back to spin 1/2 chain. So as I said, there is a range of stable critical behavior between delta equals -1 and delta equals 1. And actually, eta can increase up to 1. And actually, if you analyze the stability due to double vortex with winding number 2, exactly when eta becomes 1 is the limit of stability. So beyond eta equals 1, the system becomes unstable due to double vortex proliferation. So that is consistent with the phase diagram known from the exact solution. That solves the puzzle. And the difference between 1/4 and 1 is that here the transition is caused by proliferation of a fundamental vortex, whereas here phase transition is caused by proliferation of double vortices. That's a difference. That's basically what is noticed by Haldane's original paper. And in case of integer spins, if you rotate integer spin like a spin 1 by 2 pi, the Berry phase is 0, or you don't get any phase factor, which means that the fundamental vortices are not forbidden. So if you consider spin 1 XXD chain or something and change delta, when you hit eta equals 1/4, then the system becomes unstable and develops a gap. So that means that before you reach the isotropic Heisenberg point, you should enter disordered phase. So the Heisenberg model should have disordered ground state. That's basically the leads to Haldane gap. So that is okay. So here I gave a intuitive picture. In his original paper, he used more technical discussion, but this is basically how he reached the original Haldane gap conjecture. Okay. So what I wanted to say is that so first I explained about BKT transition, and second the Haldane gap, which might look very different, but actually historically very, very closely related. And so another interesting historical remark is that Haldane still got Nobel Prize because eventually he published a paper on Haldane conjecture, but on different content. So apparently he was not very happy with the original derivation because you first break O3 symmetry down to U1. So he tried to do something starting from O3 symmetric model. And this is a better known paper. So, okay, I'm sure now it's even larger, but when I checked this paper published in '83 using O3 nonlinear sigma model, is cited more than 2,000 times. So I assumed that, okay, in this paper, he must have discussed a topological term because this is how we know about the Haldane phase. But I checked this paper again recently, and now we can download the PDF file and the search string. And if you try to search this paper by topological or something, actually there is no single word of topological in this paper. So actually in this paper, he used a lot of different arguments. So the question still remains that how he came up with this topological term. Okay, actually in original presentation file, I was using animation, but in converting PDF, I removed animation. So now it's not so interesting now. But anyway, so this is how topological term appeared in this context. So after writing this original paper, Duncan Haldane moved to University of Southern California in Los Angeles as an assistant professor, I think. And around that time, Philip Anderson went back to Bell Labs, and there was a 60th birthday party celebration for Philip Anderson. So Duncan flew back to East Coast and attended this party. And then, after the party or something, Philip Anderson offered Haldane to drive to Princeton or something, and then they went to Princeton. And then according to Duncan, he talked about this. So at that time, he didn't know about topological term and so on, but he explained what he found to this guy, Edward Witten. And then Witten answered, okay, maybe what you are doing may be related to topological term. Then Duncan went back and then tried to calculate. Then indeed he found a topological term in Lagrangian formulation. He started from Hamiltonian formulation, but then it turned out that it can be described by topological term. So this is again, probably nobody knew about this. So how this is buried in history is also kind of interesting. So okay, so I tried to find the original literature, and actually this paper in '85 appeared in Journal of Applied Physics. I think was the first in the literature which contains this topological theta term in the context of this spin chain and Haldane gap. So here there is a clear statement. The quantum Heisenberg antiferromagnet can be described by O3 sigma model with topological theta term, blah, blah, blah. And theta equals to 0 pi related to integer and half integer spin and so on. So this short abstract contains basically essentially the Haldane conjecture. But this paper is also probably not known widely, because if you go to library, you can find this paper. Well, not really paper, because this is only abstract. And just below this abstract, there is another abstract. So apparently this issue of Journal of Applied Physics is just a kind of conference proceeding for some conference on magnetism. And apparently he only submitted this abstract, not the main text. So actually I found some other papers as the proceedings contains a main text with abstract, but there are some abstract without main text. So apparently he only submitted abstract. That's why we don't know about this. So how this story of topological term, proliferated in physics community is not by Haldane himself, but by Ian Affleck, my former postdoc advisor. So he wrote this paper in '84. So he was studying the sigma model in the context of quantum Hall effect, but he came up with, he made this problem of quantum spin chain. And this is excerpt from his paper. The model is the O3 sigma model, blah, 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 and argued by mapping the model onto the large spin limit of quantum spin chain, blah, blah, blah. So in this paper, the relation between the spin chain and the topological term is very clearly presented. But of course, he said he probably heard this story from Haldane himself or maybe from Edward Witten. So he differs. Yeah, we now review this mapping using a derivation which is a combination of that in differences 11, 12. So he did cite Haldane's paper, maybe this general applied physics paper, but these original papers were never really published. So this became kind of original paper. And moreover, I think Ian wrote this review paper, which I read many times when I was a student, and still probably very useful review in '88. And I think most people worked on Haldane gap after this. Most people read this review paper, and in this review paper, he started from this nonlinear sigma model topological term story because he was from high energy physics, so this is very familiar with him. And then I think many students, physicists read this paper, so we were kind of fooled. Well, I shouldn't say fooled, but we came to believe that this was Haldane's original argument, but in fact, it was not. Okay, yeah, this is also interesting, but maybe I will try tomorrow. So yeah, to summarize the history, so this sigma model story was very popular, but this is not real history. And the real history was based on this Latin-Jarigis theory, but the original paper was rejected. And later he reformulated the problem with nonlinear sigma model, and with a suggestion by Witten, connection to topological term was found. Then Affleck spread this story by his review paper and so on. Okay, so I'm running over time, so yeah, maybe these parts, maybe I can cover tomorrow. Okay, so thanks.